All right, so we want to compute this line integral. I'm giving you the vector field F. It's a two-dimensional vector field. C is the unit circle with counterclockwise orientation. So before you dive into this, you should stop and think. In fact, that's just good life advice. You should always just stop and think about almost everything. Is this a good idea? Am I missing anything? How could I do this more efficiently? So on and so forth. So let's stop and think for a minute together. What do we notice about C? We notice C is closed. That's always something you want to pay attention to in this chapter. When C is closed, that's often good, not always. So C is closed. And I realize, hey, if I happen to know that this F was conservative, then I know what the answer is. Hopefully you do as well. I'm not going to tell you actually just yet. Hopefully you know C is closed. If F is conservative, then we know what the answer to our integral is. So the question is, how do we tell if F is conservative or not? So let's ask that. So is F conservative? One way is just to produce the potential function. But if you saw what I'm seeing, C is closed, hint, 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 then I don't actually need the potential function. I know what the answer is. All I need to know is F conservative? If it is, then I know the answer. So let's write down the first component function of F is P equals X plus Y squared. The second component function is Q equals 2XY plus Y squared. And now we're just going to check what's P partial Y, I get a 2Y. What's Q partial X? I get a 2Y. Look at that. They're the same. So now we know F is conservative. And so at this point, I can write down the answer. I can say, okay, the integral along C of F dot dr, that's just 0. Why? We should explain. Because F is conservative and C is closed. So the answer is 0, and we didn't have to parameterize C. I didn't have to find the potential function. I'm just paying attention, and I realize, hey, I really like line integrals of closed curves when the function is conservative. The function might not be conservative. You need to realize that. It may not be conservative. If it's not, you have no choice but to evaluate it the old way, at least for now, just plugging in directly. So you got to find a parameterization and plug it in directly. I shouldn't call it the old way because that you must do it the direct way. How's that? All right, let's squeeze another example into this video. We'll do two at once. So I want to work out this line integral of f dot dr, where f is the same as the previous example. The only thing we're changing is our circle is no longer going to be the unit circle. It's going to be the top half of the circle centered at the origin from radius 3. And we're actually going to start here and go that way rather than where we typically start from and go counterclockwise, just to change it up a little bit. So I've written down our old function, big F. And whoops, I need to erase some of this. I scribbled some of this out, but I want to do it with you. I've written down our old function, big F, and I need to figure out whether or not it's conservative, but we already know that. We know from last example, that it is conservative. I can't just say the answer is 0 because this curve is not closed. So now I actually do need to find the potential function. And so I'm going to do that. So I'm going to realize that that if this guy, since this guy is conservative, I can write it as a little f partial x, little f partial y. And that means that I can think of little f partial x is x plus y squared. So integrating with respect to x, I get f of xy is x squared over 2 plus xy squared plus some function g of y. I got to figure out what g of y is, so I'm going to compute f partial y from what I wrote down. From what I wrote down, f partial y is, well, this is 0, this is 2xy, this is g prime, so I get 2xy plus g prime of y. And I know now that whatever I get for f partial y has to be the same as what is right here, because that is f partial y. And so this is equal to 2xy plus y squared. Well, that's great. Now you know that g prime of y is y squared. You cancel those. And so I know that g prime of y is y squared. So g of y is y cubed over 3 plus a constant. And so that means that for my potential function, I'm running out of room. Let's see if we can squeeze it here. My potential function is f of xy equals x squared over 2 plus xy squared plus y cubed over 3. Now, you could pick any constant you want as well. I'm just going to pick c equals 0. And the point now is the integral along c of f dot dr is just this f of the ending point, f of 0, 3, minus f of the starting point, f of negative 3. Whoops, I wrote this wrong. This is not 0, 3. This is 3, 0. So f of, let's erase that, 3, 0 minus f of negative 3 to 0. Notice I didn't parameterize this. I didn't need to parameterize this. I just need to know the ending point and then the starting point. And actually, in this case, when I plug in 3, 0, 3 for x, 0 for y, I'm going to get 9 halves and then 9 halves again. So this is just 9 halves minus 9 halves, which is 0. And that's a really interesting point worth making, is that you can get 0 as the answer even when C is not closed, right? We know that if C is closed, and this line integral is of a conservative function, we're integrating a conservative vector field, then you're going to get 0. But you might get 0 in other cases as well. So let's stop this video here, and then we'll go on and do some more examples.